this morning. Thank you, Pete. It's all yours.
Great. Okay. Sound check. Can everybody hear me? You hear me, Sam?
Yes, we can. Thank you very much.
Great. Okay. Well, thank you for that. And that was fun. I'll certainly try that, but I'll try it after my presentation. Probably everyone's going off trying that now. Okay. So my name is Pete Rai. I am a principal engineer here at Cisco, and I'm going to just do a little bit of introduction to today's thing, a bit of scene setting, so you know what it's about and why we're here. So why are we here at all? What's the point of this day? Well, we're here because things are changing. Okay, and there's quite a big change taking place, and it's quite a profound change, actually. And we'll outline some of that change during the day. And it changes not only the way technology works, but the way we use it, but also it will inevitably change the way we think about ourselves and about our society as we cede more control to things which aren't of us, if you like. So what we'll try and do today in this presentation, at least, I'll try and explain to you what the change is, why it has a big impact on us all, why it involves the skills that you are learning right now, and why there's a real role to play for women to take part in this change, more so than perhaps they had a chance to do in earlier technological innovations. Okay, so here we are in the middle of 2021, still loading, as it were, and you know, hopefully better than 2020 was. And we're going to try and look forward now to see what changes will occur. But one way we can sort of make sense of the future is by looking backwards for a moment and see what's changed in the past, what's brought us to 2021. So we'll do that briefly. So the people in the audience now are 16, 17, 18 years old, and so I won't. It's not a face-to-face meeting, so I won't ask you to guess when you thought I was that age. But unfortunately, it was a very long time ago. It was in 1985. Probably seems like prehistory to the people in the audience, certainly before any of you were born. And it was another millennium ago. But let's just have a look at what's changed from the point when I was your age to the age you are now, and let's use that as a way of understanding what's about to happen. Well, this is 1985. This is what we were doing back then. This is actually the most popular television show of the time. Dallas, you might remember it. Back to the Future was the most popular movie. Wham was the most popular group. MTV had just started in the UK. It was a complete innovation. Thought you could have a channel which is just about music. EastEnders began in 85 as well, and ironically, still carrying on with some of the same people and some of the same plots, it turns out. An interesting Super Mario was released in 1985, so that's quite an old franchise. This is the original Super Mario, released again in 1985. So a lot of strange and alien things were happening in 85, but some of these you will probably still recognize today, and so they have a kind of a legacy. But two other things happened in 1985, and two things that in 1985 nobody really noticed. One was the release of the Apple Mac 1. Okay, that happened just at the end of 84, but it hit the market in 85. And one was the release of an operating system called Microsoft Windows. Okay, both of these were released in 85. Now, there's no reason the average man on the street would know what this meant. It wouldn't have been on the news. Nobody would have noticed. In fact, most people probably would have a vague idea what a computer was. But if you went to most people and said, oh, there's a new operating system, they really wouldn't even understand what you were talking about. It would make no sense to them. But nevertheless, these two innocuous things, which certainly made very much less of an impact than these things, actually were going to fundamentally change everything, really. And they were the beginning. They were an early kind of indication of things that had to change very, very radically, and had much more of an impact than the previous media I showed. Now, the idea of having a computer on your desktop, which might seem quaint now for the wrong reasons, you might think, well, that's quite a big computer, was actually quite a novel idea, because computers previously had filled whole rooms. And you might literally have an entire computer room, you know, in a university or a business. And the idea that you could squeeze all that down onto one desktop was quite radical and quite profound, just in one box. With one wire, with one mains wire coming into it. So they went from rooms to desks, and now obviously we're coming into pockets, but we'll talk about that when we look ahead. Now, the Apple Mac shipped with 128 kilobytes of memory. Now, the telephone I use now, which isn't a particularly new one, a Samsung Galaxy S9, ships with 256 gigabytes of memory. So my phone, which I just use for random platform games and email, is 2 million times, 2 million or 20 million, 2 million times more powerful than an Apple Mac 1. Oh, something's happened there. Are we still okay, Sam?
You're still
Yep,
good.
okay. So it's 2 million times more powerful than an Apple Mac 1, which is quite extraordinary. In fact, my telephone, which I use on a day-to-day basis, is 1,000 times more powerful processor and even has 32 times more screen real estate than an Apple Mac 1. So these machines were very, very crude, and a lot has changed in the intervening time. In fact, this image of a Mac, this picture of an Apple Mac 1, which I've included in this PowerPoint, this picture is 500 kilobytes. So this picture couldn't fit on an Apple One. You would need 3 or 4 Apple Mac Ones to host this picture of an Apple Mac One. It just shows you how sort of, the idea of, you can see it's a black and white screen. The idea of having a full color image would have been quite alien in those days. 2 other very, very profound things have happened since 1985. Some of you may recognize this device here. It's a compact cassette for storing music on a magnetic reel. Very, very popular in 1985. It was the principal form of music consumption in 1985. But it's analog. It's an analog form of music. It's an analog because the information is stored in an analogy. In this case, it's stored as magnetic variations on a tape, or it might be stored as grooves on a record, etc. But when I was born, everything was analog. There was nothing but analog. Okay, but when you were born, everything was digital. And you only really interact with analog media if you're kind of a hobbyist or something like that. So between you being 17, 18 and me being that, a change happened. The world switched from broadly analog ways of managing data to broadly digital ways, which means it went from non-computational formats to computational formats. In the entire history of humankind, which stretches over 5,000 years and hopefully will stretch another 5,000 years into the future, that change will only ever happen once. Okay, once you switch from an analog to a digital principal mechanism, you will stay on the digital track forever. So that happened while we were here. That was our little bit of the timeline that we saw that change. And another very profound thing happened. This is a modem from 1984. Cisco actually started in 1984. And this is one of the early cable modems. So you could use this to connect to the internet. But why would you bother? Because although there was a crude internet, there was no World Wide Web. There was nothing to connect to. There was no Facebook. There was no TikTok. There was no Snapchat. There was nothing. There was just a few bulletin boards. So that's another profound change that's happened. So we can see just from 1985, when I was 17, to today, when you're 17, a whole raft of stuff has changed. Suddenly the internet has arrived. All the media has become digital. And digital processes have taken over. And look at us now sitting in the middle of a pandemic all around the country, talking to each other as if it didn't matter. These things would have seemed unimaginable in 1985. Okay, beyond science fiction. But now let's think about the other way. Okay, so I am now presenting to a bunch of 17-year-olds, and I'm a certain age. You can do the maths. You're maths people. You can work out what that number is. When will you be my age? So I imagine in the future you're my age and you're presenting to a bunch of 17-year-olds. When will that be? Well, that'll be around about the year 2055. Okay, so in 2055, some of you may be on whatever virtual stage exists at that time, presenting to a bunch of 17, 18-year-olds and saying, well, the future is bright and rosy. But this seems like such a long way away. It seems like a future away. But when we think about what's happened since 1985, so I'm holding in my hand here a computer that's 2 million times more powerful than a standard computer in 1985. So what does it mean to have a computer that's 20 million times more powerful than my current MacBook? And it's not probably even 2 million, because not only is things changing, they change at an accelerating pace. It may well be 20 or 200 million times more powerful. And whilst it was an innovation to have a computer on a desktop, and now it's in our pockets, what's next? Where does it go? It went from the room to the desk to the pocket. Where does it head next? And does it subsume into the building, into our bodies, or whatever? A lot of things will change. And there's a major change happening. There's a paradigm shift happening. And you are essentially generation 0 of that paradigm shift. You're the first generation to take part in that paradigm shift. And that shift is the shift to AI. And what do we mean by AI? What is AI? How does AI differ from machine learning? We'll cover all this throughout the day. So today, just for this presentation, just go with me. There is a shift happening where the way that we interact with technologies and the way we use technology to solve problems is fundamentally changing. Okay, and everything that I described to you before, all the computers and the operating systems and the rooms, that's all ultimately will be seen as just the precursor to what's about to happen. That'll be the earlier history of what happened. And huge advances. Oh, I'm getting some echo.
Can you hear that, or is it?
Somebody's come off
No,
mute. So
I can hear it. I don't know what's going on. Let me have a little look. Can anybody see?
I will press on. It's gone.
Right, I've muted them.
Okay, thank you.
So huge advantages are about to get, and we can start to do things which were previously unimaginable with these kind of apps. And what we're going to do today, throughout the day, is explain what that change is and explain how it's happened, and try and explain in some concrete terms what it actually means. But let me try and do that in one slide, in a very kind of trite way. Other people will cover it in more details than this. Whereas in a traditional programming environment, you take a bunch of inputs and you have some output you want to produce, and somebody writes a program to transform the inputs into the output you desire. So let's say I have a bunch of medical signals from a cohort of humans, and I want to work out which of them are likely to get heart disease. Somebody would write a piece of software that processes that, and we would write it in a programming language like Java or Python or something. And the program, the plus here, is the thing we're creating, and the output is the thing we're desiring. And this is a very traditional approach. You're going to say, well, why is there any other way of doing it? This is the way it's always been. Well, another way of thinking about that is in a machine learning approach. So in a machine learning approach, which is just one part of AI, by the way, what happens is we take those same inputs of all the people's health records, but then we take an example set of outputs. We say, well, of this particular cohort of people with all these particular health characteristics, the following ones got heart disease. This man got it, and this lady got it, and this lady got a mild version, this man got a severe version. And we give the computer the inputs and the outputs, and we let the computer work out what the program is. So the computer learns by looking at the inputs and the outputs. It learns the patterns, and it learns what's going on, and it produces, in this case, a classifier which says, oh, okay, well, I think I can see what's going on. I can see which inputs lead to which outputs, and I've created a program myself now that does that. And so here, the program is being created by the machine. And then later on, when I give it to a person it hasn't seen before, I say, well, here's someone that wasn't in your training material. What do you think about this person? And it can give me, you can say, yeah, well, I think there's a reasonable chance this person will or won't get heart disease because it's created a program of itself. Now, in this particular instance, it's not that important whether humans understand what it's done. Like, is it important to understand the program? If its outputs are good and the outputs are valuable, can we just leave it to the machine to work out a program? Or is it important for humans to not hand over kind of nebulous control to machines so they're making decisions without us even knowing how they're doing it? Okay, so if that perhaps seems a bit abstract, let's try, oh no, I've got another slide here. I thought we moved it to last. Okay, so here's some examples of how of this in action. So handwriting recognition is a good example. So here we have some handwriting that someone's done on a tablet using a pen, and here we have the same, which has been digitized into machine processable text. Now this is a classic example of where machine learning can happen. We show a machine lots of examples of handwriting. We say this is somebody writing the word Mac Stories Weekly. This is somebody else writing it. This is somebody else writing it. We show it, and as long as we show the computer enough examples of the handwriting, and we say, oh, and by the way, this is what this means. It means Mac Stories. We label it. Eventually, the computer will say, okay, it's fine. I've got this. I think I understand what's going on. I think I can actually read this text for myself now. Now, and you can go and try this for yourself. If you go to Google TensorFlow on the Google website, actually there's a set of training material for handwritten digits, and you can actually go ahead and interact with that and try and get the computer to learn to read handwritten digits. Now, when the computer does this, it doesn't really understand what it's doing. I don't want people to think we're talking about a computer that's becoming generally intelligent. It's not. The computer just sees lines and vectors. It doesn't see anything else. It says, okay, well, for this given set of lines, vectors, lengths, colors, I think it means this thing. It doesn't really have a human understanding. When you read this text here, you have a general understanding of the text. In fact, you can't separate your general understanding from your interpretation of the text. When you look at the characters, you don't just look at it and translate it. You think about what it means. It has the word Disney in. It's a story of somebody. They said there it's a Mac story. It has a date, so it's week 50. So he probably went. Maybe there's 49 earlier articles, and he's got very messy handwriting. So you might make some judgments about that. You can't separate your human self from the process, but computers can because they don't have a human self. They simply see vectors, lines, and they simply interpret those in the way we ask them to interpret them. So now we're going to try and build a classifier right now, live on stage, in this virtual stage at least. Okay, so how are we going to build a classifier? Well, I'm telling you that all these images are of the type called foo. Now you're going to say, well, I don't know what a foo is, and I don't know what these images mean. And I'm going to say to you, don't worry about that. Just go with it. Look at these images, and I'm telling you, this is a foo. Okay, and then look at these images, and I'm telling you that this is a bar. Okay, bar means nothing as well. You're going to say, I have no idea what these labels mean. It's fine. I'm not asking you to understand the labels. I'm simply saying that these things on the left here are foos, and this thing on the right is a bar. Now, if I show you an image and I say, is that a foo or a bar? You could look at this and say, well, that's clearly a bar. I can tell you that's a bar. It's much more like a bar than a foo. And if I show you another image and I say, is this a foo or a bar? You can say, well, that's very much a foo. Okay, it's a better foo than the example foo you showed me. It's got a lot of foo-ness. It has a trait of foo-ness about it. Okay, and then we can go to slightly more difficult examples. I would say on balance, this is a foo. This is a bar on balance. Okay, this is a tough one. Is it a foo or a bar? It's probably a foo, I would say, although there's some ambiguities here. This one's even more ambiguous. Okay. What's going on here? Well, you didn't understand the images and you didn't understand the labels. You had no real world understanding of what that meant. And that's the situation the computer is in. It has no real world understanding of anything, okay, because it hasn't got general intelligence. It has narrow intelligence. But that's okay. As long as you give it enough examples of a foo and enough examples of a bar, it can create a classifier and it can say, oh, I can be pretty good at identifying foos and bars. So what we did here was, in your mind, I created a classifier for a foo and a bar, and a physical structure has got created in your mind now, an actual physical thing in your mind now for classifying foos and bars. It's a completely useless structure that you'll carry with you for the rest of your life, I'm afraid. But there it is. We created a classifier over something we don't understand, and that's what's happening inside a computer when we give it machine learning. It seems to be intelligent and it can look at things and say, oh, that's definitely a foo, but it doesn't really have a general understanding of what that means. Now here we have two images and two shapes on a 2D plane. Okay. If I showed you 3 images and 3 shapes in 3D and asked you to produce a classifier for the 3 of them, you might say, oh, that's going to be a bit tricky, but I can probably still do it. Okay, you can probably say, well, I'll need a bit more training material, but I can eventually make a classifier in my mind for that. If I gave you 100 shapes in 100 colors in 100 dimensions, at this point you would say, well, that's just stupid. You know, I can't think beyond 3 dimensions. I'm a human encapsulated in space and time, so I can only see 3 dimensions. Besides, I can't even process 100 colors either because my eye doesn't stretch to that. Well, that's because you, as a human, you suffer from human failings and you suffer from human restrictions, but the machine does not. We can absolutely train the machine to recognize 2-dimensional foo bars, but we can absolutely train the machine to recognize 100-dimensional foo bars in 100 colors. And that's because machines aren't subject to the same failings as humans. They don't have a brain like ours, and it's much more versatile. If you're on stage now, I'd ask people to tell me what these people have in common, but we're not on stage, unfortunately. But have a think about what these people have in common, and I'm going to tell you that the answer is that what they have in common is none of these people exist. These people aren't people at all. These aren't photographs of people. These are drawings done by a computer. These people, not only do they not exist, they never existed. Okay, these are simply drawings done by a computer. Somebody showed a computer millions of photographs of humans And eventually enough training material built up that the computer said, oh, I think I can see what a face is. I've got this. I know what a face is. I've seen enough training material to know what a face is. And we could say, okay, well, if you know what a face is, draw one at random. So it just draws this. So none of these people exist. They don't exist. They're not actual people. And you might say, well, that seems remarkable because they look like people to me. And this is an example of how AI is kind of bending the way we think about ourselves. If I took you to the National Gallery, portrait gallery in London, and we went round and I showed you paintings, you wouldn't think that was remarkable. You wouldn't say, oh, wow, this is remarkable. Someone's made a painting. But for some reason, these paintings seem different to us. And the reason they seem different is not because something's changed fundamentally, it's because of the fidelity. The fidelity of this drawing is immensely detailed. And so much so that it looks as if these are actual photographs, okay? So, and this is an example of where computers can leapfrog what humans. This is a perfectly good illustration of what I said earlier about dimensionality. When a computer makes a painting, it can make a painting which is so indistinguishable from the real world because it's able to process information on a much vaster scale than humans are able to. And if you go on to thisisnotaface.org, in fact, I think this is not a thing.org, where you can see lots of not just paintings, but music and speeches and other things which have been automatically generated by machines. Okay, so let's talk a little bit about why we need machine learning and where machine learning comes in. And let's think about programming a certain number of games. So this is noughts and crosses. And if we wanted to write a computer program to play noughts and crosses, it wouldn't be too hard because it's not that complicated. In fact, the best way to write a computer program to play noughts and crosses is simply to make a list of all the possible moves there might be, and simply in that list, simply to have the best next move. Okay, there's only 255,000-ish possible combinations of a tic-tac-toe, as the Americans call it, grid. So we would just list out all those in a table and we'd say for any given state, this is the best next move, okay? And we would just, and then when someone made a move, we would just look it up in the table. We would say, oh, where is it in the table? Oh, this is number 1012. The next best move is this, okay? Very simple, yeah, it's a simple lookup. Then we come to a slightly more complicated game like chess. Now in chess, there's too many combinations to do it that way. If we tried to make a table of all the possible combinations on a chessboard, you know, the table would be bigger than any computer we could possibly hope to store it in. It would be billions and billions and trillions of rows. So we can't do that the same way. We can't make a big table. But for any given position in chess, as we have here, there's not many things that can happen next. So from here, from this given position, maybe there's about 20-ish next moves that are possible. Not all moves are obviously possible, only about 20. And then if 20 moves are possible, then from each of those states, let's say roughly another 20 moves are possible. So we have 20 times 20 times 20 moves. And so what we can do is, instead of forming a list, we can form a tree of possibilities. We can say, okay, well, there's 20 possibilities from this point. And if I step forward onto the next one, there's 20 or so from that one. And then eventually I end up with a tree of possibilities. And how far forward in that tree I go is how far forward, how many moves forward I'm thinking, okay? And that's exactly how computers go about solving chess problems traditionally. So, and computers overtook humans at chess in 1997 when IBM produced a program called Deep Blue, which beat the then reigning chess champion Garry Kasparov in chess, who was our best chess player. Now, Kasparov possibly does think 6 or 7 moves ahead. Because he's a genius. You know, most of us probably can think 2 or 3 moves ahead, and Kasparov was maybe thinking 6, 7, maybe he was thinking 8 or 9. Well, Deep Blue was probably thinking 50 or 60 moves ahead. It's like you can't outpace the machine again. So, you know, humans lost chess to computers before the turn of the century using this tree-based approach. But now we come on to this game, Go. So this is a game that's very popular in China and Japan and Korea and places like that. And now the number of combinations isn't even possible to put into a tree structure. Even the tree would explode. Like the number of possible moves from this one is like hundreds, and then the next layer is hundreds again. So the tree would very quickly explode and become non-computational. And you would need like more than the age of the universe to be able to process Go that way. And this is where things change, because there's a flip here between chess and Go. Between chess, we do things in traditional software sense, and between Go, we had to switch to a new way of doing it. So instead of trying to program a computer to play Go in a traditional what happened was a team at DeepMind in the UK, UCL, I think, produced a program called AlphaGo, which learned to play Go. So again, as we said, we gave it lots of training material. We said, well, this is a game of Go, and this is a game of Go, and this is a winning game, and this is a losing game. And the computer just played loads and loads of games, and it built its own program for playing Go. And it actually learned, I think, by playing itself a number of times, and millions and billions and millions of times. So again, if you remember back to the drawing I said, where rather than having inputs, writing a program, and then getting the desired outputs, as we were here, now we're giving it inputs and outputs and say, well, why don't you work out the program for yourself? And that's exactly what happened. And AlphaGo in 2016, I think, beat the reigning human Go champion in quite a stunning way, and played by, I'm not a Go player, but by all accounts, not only played a good, but played quite a beautiful game, was the way it was described. And finally, we come on to this guy, poker. So what about poker? Because poker is quite different from the other games because it involves two things. It involves hidden information, so not all information is revealed to all players, and it also involves deception. It involves deceiving the players into thinking you have more than you have. So perhaps this is a wholly human game. Well, unfortunately not. Already we are saying AI that can play poker, online poker very well. Online poker is not quite full poker in that you can't necessarily see the other players, but so that's quite good. But even poker at a table with a computer, watching people's faces, looking for tiny micro gestures in their faces to see if they're lying. You know, the infamous poker face, as we know from Lady Gaga. Are they giving away little bits of signals about? So even poker, I think, will fall to machines in the near future. So what does this mean? Well, I think we're seeing that what computers can achieve when we give them these choices is quite immense, and we're seeing a complete revolution. And when I said that everything that happened before will be seen as prehistory, I wasn't just being idle in that. I honestly think that's what it will be. In medicine, we are already seeing computers looking at retinopathy and MRI scans and spotting cancers at rates that human experts would do the same, and I'm sure will surpass human experts very soon. In social sciences, we're seeing all sorts of stuff. We saw an algorithm that was able to give indications of suicide risk based upon people's behaviors and what they've been typing, etc. In transport, we obviously see the rise of self-driving vehicles and the ability for vehicles to take their own journeys and us to just act as sort of human passengers in that. And that'll be a much safer world. You know, 4 people a day die in the UK on the roads. And that's not even putting in place all the people who are maimed. In conservation, we ourselves put in some stuff to help spot poachers of rhinos, and that was very, very successful, and no rhinos were killed since that technology went in. So there's lots of different types of use cases that we can use for this kind of thing, where we can use computers to learn for themselves. But there is a danger. And what is the danger? Well, the danger is that humans are programming these computers. We are the ones putting them on. So we're in danger of giving the computer our own biases and letting the computer make decisions which are really a function of our own biases as humans. And we see some examples of that already. So here somebody put in a blink detector on a camera, but they didn't think about all the different eye shapes that exist around the world. So that was, you know, it's not the computer's fault, it's the fault of the people who created the training set for that particular thing. This is about whether people are given a loan or not. And it turns out that that was, although it was being decided by a computer, it was deciding it on racial lines, simply because the training material they'd given it was that way. And similarly, things like high risk of crime, we've seen that's been very badly used in the US and very badly programmed or very badly trained already. There's an area called recidivism. And Amazon had a recruiting tool which was very biased against women, even though the gender wasn't present in the CV. It indirectly works out what was going on, etc. So these are 4 very negative examples, but I don't want people to think that AI itself is negative. What these examples show us is it's not enough just to rely upon the computer. We have to think very hard about what it is we're asking the computer to do and how we go about training the computer to do that. Think of the computer as a super able child Now, we train children through education, a process you're on, to do things for society. Now, if we gave that child a very narrow education, then obviously is likely to pick up the biases of its trainers or its parents. And so it's very important that when we train computers to do things and then we ask them to do consequential things like judge us in courts, decide whether we should have medicines, decide whether we're allowed to have mortgages, it's very important that those computers are trained responsibly. And one aspect of that is to make sure a wide spectrum of people are involved. And it isn't just where we've ended up, unfortunately, with software engineering, a broadly male concern. So, and this isn't just, you know, an idle thing. It's actually very likely to become a skills crisis for our industry, that we will want to hire people from a broad range of backgrounds to help us bring these training models together and bring as many voices into the room. And this is why there's a really good opportunity, I think, for people to get involved at this stage, because we're still very early on in this technology. Okay, so that's my talk. So what did I say we were going to learn? I said we were going to learn what change has taken place. Hopefully we've seen that. It's a shift from traditional software programming to machine learning and AI, and what impacts that has. Well, suddenly it has an impact that we can tackle use cases on a scale, fidelity, and size that we couldn't possibly have imagined before. And that means that lots of society's biggest problems are suddenly coming into scope, and we can solve those. That there's a role for your skills. I didn't go through the maths of it, but you know, when you build these models, and we'll see later on when you do that, it's really mathematics, not computer science, which is important. It's not really important whether you understand how to program a computer as much as it is that you understand geometry and algebra and you know, topology and calculus and probability and matrices, all those kind of things you're learning now. And so it involves your skills, but it also involves your as a community, it involves your gender, it involves your sex. We need to involve more people in that, and we certainly need to come to a much better gender balance going forward than we ever had in the past. Okay, so that's my introduction. Hopefully I was on time. Are we taking questions, Sam, or are we straight over to the next speaker?
I think we're going to have to move straight on. Although if people do have questions for Pete, you can always put those in the chat and we can make sure that Pete gets those questions. If we have an opportunity today, we can respond to some of those, but it may be that we'll have to put something together afterwards, Pete. But yes, right now, thank you very much for that introduction. That was great. We've got a good sort of basis of understanding perhaps where we're going now.